Hey guys, here's your notes on Newton's first law of motion. Um, you already have Newton's first law written in your notebooks, so what we're just going to do is review how that applies to net force in this video. This video focused on net force. Um, so what I have in front of you right now is just a little review of the basics of Newton's first law. You know that it says that when objects at rest remain at rest. You don't have to write this down. You already have the law in your notebook. Objects at rest remain at rest, and objects in motion remain in motion. But when does this happen? Because it doesn't always happen, obviously, in real life. So in what case do objects have inertia, keep doing what they've been doing? The law says, in the absence of a net force. You could read that in your own notebook. Or when F net equals 0. Well, what does that even mean? That means when the forces add up to 0, the positive and the negative forces balance out and cancel out to 0, that's when objects remain at rest. That are at rest, or objects in motion stay in motion at a constant speed in a straight line. Only when all the positive and negative forces balance out to add up to 0. All right, and you have to draw a force diagram to see if that is the case. All right. So there's two forces we're going to deal with on our force diagrams. Write this down. You've got FP, which is a applied push or pull. We call it FP because P is the first letter of push or pull. You've also got FF, force of friction, and it always acts opposite the direction of an object's motion if that object is moving, or it acts opposite of the direction of FP when you try to or intend to move that object, right? Any object, if you push it in one direction, friction will push back in the opposite direction. We have a little diagram here which shows you V, if the object is moving to the right, friction will be acting on that object to the left. It's called a force diagram, and that is an official part of problem solving when it comes to forces, so you got to get used to drawing them now. Just draw yourself a little box or a little object, and you could draw all the directions of forces coming out of the center of that object right there. If you want to indicate the direction of motion of an object, then you do it to the side of that box. You don't do it on the box, just to the side. Alright. So net force. Let's start applying Newton's first law and how net force applies to it. Okay, objects at rest. So say I have a vase, or vase, whatever you want to call it. Instead of drawing a box, I'll try to draw my best vase. And you push it to the right. So FP is applied to the right. And say you push it with 5 newtons of force, right? So the vase is at rest on a table, and you just touch it with your fingers slightly. 5 newtons is not a lot of force, and you think, oh, well, there's a force. Well, it should budge from rest, but you know, based on experience, just because you touch something and you push it doesn't mean it's going to move. So why doesn't a vase move if you push on it lightly, with 5 newtons of force? It's a good thing that doesn't happen. Well, the bottom of the vase is gripping the table and keeping it from budging. What's that force called that keeps the vase from budging and grips it to the table? Right, it's friction. So friction, what is the direction of friction, you think? Well, friction acts in the opposite direction you always push. But the big question is, if it doesn't budge, it means it remains at rest. How much is friction? Well, we know based on Newton's first law, objects at rest that remain at rest have a net force on it of 0. So if I apply a positive 5 push to the right, so you gotta get it better, make a big positive sign. To the right means positive in our diagram. Then, to balance that out, friction must apply an equal amount, but just in an opposite direction to keep it at rest. Because positive 5 and negative 5 add up to 0. So objects that remain at rest, that are at rest and remain at rest, Newton's first law says automatically no net force. How do we get that with this vase? Push of 5 means friction pushes back with 5. And 5 plus negative 5 is 0. No net force. Now, what if I took that vase and I just pushed a little bit harder? I really don't want to break the vase. I might be able to push with 10 newtons, a positive 10 newtons.